Somewhere in the southern sky, about 5,000 light-years from Earth, there is a place colder than outer space itself. Not a laboratory, not a controlled experiment. A dying star, shedding its outer layers into the dark, producing something that should not be able to exist. The background temperature of the universe, the faint afterglow of the Big Bang still washing through all of space, sits at about 2.7 degrees above absolute zero. That is the floor. That is as cold as the cosmos gets. The Boomerang Nebula is colder than that, 1 degree above absolute zero. Colder than the universe itself allows, by any standard model we had before we found it. When astronomers first confirmed that number in 1995, some of them assumed the measurement was wrong. You check the equipment, you run the calculation again. You look for the error because the alternative, that a dying star had somehow cooled its own outflowing gas below the ambient temperature of space, had no clean explanation in any textbook written up to that point. The equipment was fine. The calculation was right. The boomerang was doing something that broke the framework, and the cold was only the first problem. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. The shape is wrong. A nebula this size, produced this way, should expand roughly outward in all directions and settle into something close to a sphere. The boomerang does not do that. It has two lobes, stretched outward in opposite directions like an hourglass caught mid-pour, and the geometry of those lobes has resisted every simple explanation astronomers have offered for it. The mass loss is catastrophic. In the last 1,500 years, this object has shed roughly 1.5 times the total mass of our Sun. No other known star in its class loses material anywhere close to that rate. Something is driving this, something with enough energy to strip a star down to its core in what amounts to an eye blink of cosmic time. And what that something is has not been fully settled. There are leading theories. There is strong evidence pointing in a specific direction. But the answer, when it finally came into focus, was stranger than the cold temperature alone suggested. The Boomerang Nebula has been hiding something, and what it has been hiding changes how we think about the deaths of stars. To understand why what you are about to hear is strange, you need a picture of what a nebula actually is. The word itself comes from Latin, meaning cloud. And that is roughly what a nebula is, an enormous cloud of gas and dust drifting through interstellar space. But the category covers a remarkable range of objects, and lumping them together under one word is a little like calling both a thunderstorm and a light morning fog the same thing, because both involve water. The physics at work inside different nebulae are not remotely similar. The conditions that create them are not the same. Even the basic question of what they are made of shifts depending on which one you are looking at. Start with emission nebulae. These are the ones that show up in all the calendar photographs. Vast glowing regions of hydrogen gas energized by young, hot stars burning inside them. The stars pour out ultraviolet radiation so intense that it strips electrons off surrounding hydrogen atoms. When those electrons fall back into place, they release energy as light, predominantly in the red part of the spectrum. The Orion Nebula is an emission nebula. So is the Eagle Nebula, where the famous Pillars of Creation photograph was taken. These are stellar nurseries, places where gravity is pulling gas and dust into clumps that will eventually ignite as new stars. They are loud, hot, and bright. Reflection nebulae are quieter. They don't emit their own light, they borrow it. A reflection nebula sits near a star but doesn't have the energy input to ionize hydrogen on its own, so instead it scatters the starlight passing through it. The result is a soft blue glow, because dust particles scatter shorter blue wavelengths more efficiently than longer red ones. The Pleiades cluster is surrounded by reflection nebulae, stunning to look at, but physically simple in terms of what's happening inside them. Then there are supernova remnants. These form when a massive star reaches the end of its life and detonates. The explosion sends a shockwave outward at thousands of kilometers per second, sweeping up surrounding interstellar material and heating it to temperatures of millions of degrees. The Crab Nebula is the leftover from a supernova that Chinese astronomers recorded in 1054. It is still expanding today, more than 970 years later, moving outward at roughly 1,500 kilometers per second. Supernova remnants are violent, asymmetric, and rich in heavy elements forged during the explosion. When that shockwave eventually slows and dissolves into the surrounding medium, those heavy elements stay behind, seeding future star systems with the raw material for planets and, eventually, chemistry complex enough to matter. The category most relevant to what comes next in this story is the planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. William Herschel coined the term in the 18th century because these objects looked vaguely round and disc-like through his telescope, superficially resembling the planets Uranus and Neptune. The name stuck. What a planetary nebula actually is: the shed outer layers of a dying star that was similar in mass to our Sun. When a star like that runs out of hydrogen fuel in its core, it swells into a red giant, its outer envelope puffing outward over thousands of years. Eventually, those outer layers detach entirely and drift away into space. What remains at the center is a tiny, extraordinarily hot remnant called a white dwarf. The white dwarf radiates ultraviolet light that ionizes the escaping gas, making the whole surrounding cloud glow. That glowing shell is the planetary nebula. Most planetary nebulae fit our models well. They form on timescales we can calculate. Their temperatures, their expansion speeds, their chemical compositions, all of it falls within ranges that stellar evolution theory predicts. You can write down equations, plug in the mass of the original star, and get answers that match what telescopes actually observe. There are hundreds of known planetary nebulae in our galaxy, and the vast majority of them behave the way the textbooks say they should. Astronomers can look at one and, in broad terms, read its history. How old the central star was, how much mass it shed, how long ago the ejection event began. The physics is settled enough that planetary nebulae have become tools for measuring distances across the galaxy because their peak luminosity are consistent and predictable. That predictability is why the strange ones stand out so sharply. When a nebula produces measurements that fall outside the expected range by a factor of 2, that is unusual. When the measurements fall outside by a factor of 10, that is a signal. When everything about an object, its temperature, its shape, its mass loss rate, the speed of its outflow, sits at the extreme edge of what physics should permit, or beyond it, then you are no longer looking at a variation on a theme. You are looking at something the model was not built to explain. This matters beyond the object itself. Strange nebulae are not just curiosities to file away in a catalogue. They are the specific places where the gap between what we understand and what actually happens becomes visible. Every time astronomers have found a nebula that refused to behave and then figured out why, the answer expanded the model. It added something that had been missing. The strange objects are not noise in the data, they are the signal. The Boomerang Nebula sits at the far end of this spectrum, not slightly anomalous, not pushing the edges of the model in an interesting direction, sitting in territory where the standard model of stellar death has essentially nothing to say, producing conditions that have no known analogue anywhere else in the observable universe. Its temperature alone puts it in a category of 1. But the temperature is only the beginning of why it matters. The strangest nebulae are not the ones that are hardest to see. They are the ones that refuse to fit the picture we have built for them. The Boomerang Nebula was found almost by accident in 1980 by 2 astronomers working at a telescope in New South Wales who were not specifically looking for it. Keith Taylor and Mike Scarrett were conducting a survey at the Anglo-Australian Telescope, cataloguing faint objects in the southern sky, when something in the constellation Centaurus caught their attention. It was not dramatic. There was no flash of recognition, no immediate sense that they had found something extraordinary. What they saw was a faint, elongated smudge of reflected light sitting quietly in a field of stars, roughly 5,000 light-years away. It was unusual enough to write down. It was not yet unusual enough to change anything. The shape was what got them. Most nebulae, when you catch them in reflected light, tend toward the roughly spherical. Shells, rings, disks. These are the natural geometries of gas expanding outward from a central source in all directions at once. What Taylor and Scarrett found did not look like that. The object was stretched along one axis in a way that seemed almost deliberate. When they sketched it out and looked at the rough outline, someone made the comparison to a boomerang, and the name stuck. That is how quickly informal astronomy works. A faint smudge in a catalogue gets a nickname before it gets an explanation, and the nickname outlasts almost everything else. Decades later, when the object was making headlines in astrophysics journals, it was still the Boomerang Nebula, named in a moment of casual pattern recognition by 2 observers who had no idea what they were actually looking at. Early observations were limited by what the instruments of 1980 could actually do. The Anglo-Australian Telescope was one of the most capable in the Southern Hemisphere at the time, but capable in 1980 meant something very different from capable today. The data Taylor and Scarrett had was enough to establish that the object existed, that it had an unusual shape, and that it was a reflection nebula, meaning it was scattering light from a central source rather than emitting its own. That last point was itself a small clue. Reflection nebulae are typically cooler than emission nebulae. They do not glow on their own. The light passing through them is borrowed. But in 1980, that detail did not raise any particular alarm. Reflection nebulae are common enough. Strange shapes are common enough. Boomerang went into the catalogue as an interesting object and stayed there. Through the early 1980s, the object collected occasional attention, but not the kind of sustained focus that rewrites textbooks. Astronomers who came across it in the literature noted the unusual morphology, A few papers mentioned it in passing. The central star was identified, a highly evolved object, likely an asymptotic giant branch star in the late stages of its life, shedding material into the surrounding space. This fit a recognizable pattern. Dying stars of this type are known to produce planetary nebulae, and the Boomerang looked like it might be a protoplanetary nebula, a stage in that transition before the central remnant grows hot enough to ionize the gas around it. That classification made the object understandable. Protoplanetary nebulae are strange-looking by nature. Apes are often asymmetric, often elongated, often bipolar. The Boomerang's unusual outlines seemed less surprising once you put it in that category. The problem with that reasoning was that it closed a door before anyone had looked through it. Classifying an object is a form of explanation, and explanation discourages further questions. If the Boomerang was a protoplanetary nebula with a bipolar shape, then the bipolar shape had an expected cause. The central star had a predictable future, and the whole thing could wait its turn in the line of objects worth studying more closely. Southern Hemisphere objects with no obvious anomalies in their spectral data were not exactly competing for telescope time in the late 1980s. The queue was long. The Boomerang waited. What follow-up work did accumulate through the late 1980s and into the early 1990s added texture without adding alarm? The bipolar structure was confirmed and better mapped. The outflow of material from the central star was measured more precisely. The central source was studied in more detail. None of this produced a number that stopped anyone cold. The outflow looked fast. Faster than typical, perhaps, but the error bars on early measurements were wide enough that fast could still be explained away. Astronomers are trained to distrust dramatic readings until they have been confirmed by independent methods, and in the early 1990s, the Boomerang had not yet generated a reading dramatic enough to demand independent confirmation. What the nebula needed was a different kind of measurement. Optical observations, the kind Taylor and Scarrett had originally made, reveal shape and scattered light, and some basic spectral information. They do not tell you temperature in any direct or precise way. To measure the temperature of cold molecular gas in an outflow, you need radio or millimeter wave observations. You need specific spectral lines from molecules like carbon monoxide that behave as thermometers when you know how to read them. That technology existed by the early 1990s, but it had not yet been pointed at the Boomerang with any serious intent. The object had not yet done anything to earn that level of scrutiny. That changed in 1995, when two astronomers decided to look at the Boomerang's molecular emission lines and measure what they found there. By that point, the nebula had spent 15 years sitting in catalogues, collecting a modest bibliography, carrying a name borrowed from a casual visual impression. Nothing about its reputation suggested what the measurement was about to show. At that point, the Boomerang was an interesting shape in a catalogue of interesting shapes, and no one had yet done the measurement that would make the entire astronomical community stop and stare. To call something cold in space requires some context, because space itself is extraordinarily cold. If you floated a thermometer out beyond the atmosphere, away from the sun's radiation, and let it settle into the ambient temperature of deep space, it would eventually stop falling at around 2.7 Kelvin. That number, 2.7 degrees above absolute zero, is not arbitrary. It is the temperature of the cosmic microwave background radiation, the faint, stretched afterglow of the Big Bang, still radiating in every direction across the entire observable universe. There is nowhere you can go in space and escape it. It fills the cosmos like a bath of ancient light, too cold and too faint for human senses to detect. And for a long time, astronomers assumed that no naturally occurring object could be colder than it. The background radiation heats everything it touches, and it touches everything. That assumption held until 1995. In that year, two astronomers named Raghvendra Sahai and Lars-Åke Nyman pointed a telescope at the faint, elongated smudge in Centaurus that had been catalogued as the Boomerang Nebula. They were using the SEST, the Swedish ESO submillimeter telescope, a 15-meter dish sitting at an altitude of 2,400 meters in the Chilean Atacama Desert. A dry, high site chosen precisely because water vapor in the atmosphere absorbs the kind of millimeter wave signals they needed to detect. They were not setting out to break any records. They were following up on earlier observations that had flagged the boomerang as unusual, trying to characterize its gas more precisely. What came back from the data was a number that neither of them had expected. Roughly 1 Kelvin, 1 degree above absolute zero. To understand why this stopped people cold, you need to know how the measurement was actually made. Sahai and Nyman were not pointing an infrared thermometer at the nebula. Temperature in a gas cloud is measured through the behavior of molecules, specifically through a technique involving molecular absorption lines. The gas inside the boomerang contains carbon monoxide, the same molecule that makes car exhaust toxic, and at different temperatures, carbon monoxide absorbs and emits radiation at very specific frequencies. The pattern of which frequencies are absorbed and which are not acts as a fingerprint for temperature. It is the same principle behind how a forensic chemist identifies a substance by its spectral signature. The physics behind it is well established, tested in laboratories on Earth, and confirmed in dozens of other astronomical objects. When the carbon monoxide lines in the boomerang spectrum came back, they pointed to a temperature sitting below 2.7 Kelvin. Colder than the background, colder than space. The cosmic microwave background radiation was doing something specific in this measurement. Astronomers used it as a reference light source. The background radiation shines at a known temperature, and the cold gas in the boomerang was absorbing some of that background light before it reached the telescope. The depth of those absorption features told researchers how cold the absorbing gas had to be to produce that signature. For the absorption to look the way it did, the gas had to be cooler than the source it was blocking. The source was the cosmic background itself, so the gas had to be colder than 2.7 Kelvin. That was not an inference. That was a direct consequence of the measurement geometry. When the result came out, the reaction in the astronomical community was not immediate celebration. It was skepticism. Scientists reached for alternative explanations. Could the carbon monoxide abundances be unusual in a way that mimicked a cold temperature signature? Could there be some problem with the calibration? Was the background radiation somehow being scattered or distorted before it reached the telescope? Sahai and Nyman went back through the data. The result held. Other researchers examined the measurement. The technique was sound. The number, approximately 1 Kelvin, kept coming back. What it meant was genuinely difficult to absorb. Absolute zero Kelvin, is not just very cold in the ordinary sense. It is the point at which all molecular motion stops, the theoretical floor of temperature, the place where thermodynamics says nothing can go further. Everything above absolute zero has some thermal energy, some motion in its molecules. At 1 Kelvin, there is barely any. The Boomerang's gas was sitting at a temperature where almost nothing moves. This was happening not in a laboratory cooled by liquid helium and vacuum pumps, but in a cloud of gas expanding outward from a dying star, in open space, with no equipment and no engineering, just physics running at an extreme that nothing else in the known universe had reached. The questions it raised were immediate and uncomfortable. How does a dying star produce gas this cold? Normal stellar outflows are warm. Even the coolest nebulae known at the time were sitting at temperatures of tens of Kelvin or more. The background radiation alone should have been keeping the Boomerang's gas warmer than this. Something was removing heat from the gas faster than the background could replace it. That something had to be a physical process operating at a rate and a scale that had no precedent in any other observed object. The size of the Boomerang's cold region, the speed at which the gas was moving outward, the rate at which the central star was losing mass, all of these had to be threaded together into an explanation that nobody had ready in 1995. Nobody had needed one before. Astronomers who had glanced at the Boomerang as an interesting shape in a catalogue now looked back at it with very different eyes. This was not a curious elongated nebula. This was the coldest known place in the observable universe, and the mechanism producing that cold was sitting undiscovered at its center, 1 degree above absolute zero in a dying star's outflow, billions of miles from anything. And when astronomers checked the numbers again, the numbers said the same thing. The way the Boomerang reaches its extreme temperature is not magic, it is physics, but physics operating at a scale and speed that has no parallel anywhere else in the known universe. Start with something familiar. You have probably picked up an aerosol can after using it for a few seconds and noticed it felt cold in your hand. That is not a coincidence. When pressurized gas escapes through a nozzle, it expands rapidly, and as it expands, the molecules spread apart. They have less energy per unit of volume. The temperature drops. This is not a chemical reaction or anything exotic. It is simply what gas does when it is forced to occupy more space very quickly. Physicists call it adiabatic cooling, and it shows up everywhere from spray cans to refrigerators to the breath you exhale on a cold morning. The same principle governs what happens inside a refrigerator. A refrigerant gas is compressed, then allowed to expand suddenly, and that expansion pulls heat out of the surrounding environment. Engineers have been exploiting this effect for over a century. It is one of the most reliably understood processes in thermodynamics. Now take that principle and scale it up by a factor that almost breaks the imagination. When a dying star sheds its outer layers, the gas it ejects doesn't drift away slowly, it gets launched. In most cases, stellar winds move at tens of kilometers per second, which is already fast by any human standard. The Boomerang's outflow moves at around 164 kilometers per second. That is roughly 590,000 kilometers per hour. A passenger jet crosses the Atlantic in about 8 hours. The Boomerang's gas would do it in about 20 seconds. At that speed, the expanding material reaches vast distances very quickly, and as it spreads outward into the space surrounding the star, it undergoes exactly the same process as the gas escaping the aerosol can, just at a scale that covers billions of miles instead of a few centimeters. The faster the expansion, the more dramatic the cooling. This is where the Boomerang starts to look different from every other object of its kind. Most planetary nebulae and protoplanetary nebulae don't cool down to anything close to absolute zero, even though they are also ejecting gas rapidly. The reason is radiation. The central star is hot, often extremely hot, and it bathes the surrounding gas in ultraviolet light. That radiation heats the ejected material. The cooling from expansion and the heating from the central star reach a kind of balance, and the gas settles at temperatures that are cold by human standards, but nowhere near the extreme low end of the scale. In most nebulae, the central star wins that fight. The gas stays warm enough to glow. That is what makes nebulae visible in the first place. The Boomerang is different because the race is not even close. What matters here is not just the speed of the outflow, but the amount of material moving at that speed. The Boomerang is shedding mass at a rate of roughly 1/1000th of a solar mass per year. Written out as a ratio, that doesn't sound alarming, but consider the context. Other asymptotic giant branch stars, the same category of dying star the Boomerang belongs to, typically lose mass at rates 10 to 100 times slower. The Boomerang's mass loss rate is the highest ever measured for any object of this type. The sheer volume of gas pouring away from the star creates a thick, dense outflow. That density matters because it means the gas is opaque. It blocks the radiation coming from the central star. The ultraviolet light that would normally heat the surrounding material cannot penetrate the dense stream of outflowing gas effectively enough to counteract the cooling. So you have gas expanding at 164 kilometers per second, in quantities no other star of this kind produces, dense enough to shield itself from the star's radiation. The expansion cooling runs ahead of the heating. The temperature drops and drops and keeps dropping until it reaches 1 degree above absolute zero, colder than the ambient temperature of the universe itself, which sits at about 2.7 Kelvin because of the cosmic microwave background, the faint thermal afterglow of the Big Bang still present everywhere in space. There is something almost difficult to accept about that. The background temperature of the universe is not zero. Space has a flaw. The Big Bang heated everything, and even after 13.8 billion years of cooling, the universe still has a residual warmth that fills every corner of it. To be colder than that background means the Boomerang is not just cold in the way that deep space is cold. It is colder than the universe's baseline. It is an exception to the general thermal state of everything. The mechanism behind it is the expansion cooling, but the expansion cooling only reaches those depths because of the mass loss rate. That is the key variable. Reduce the mass loss and the outflow thins, the radiation penetrates, the gas heats up, and you get a normal nebula. The extreme cold is a direct consequence of the extreme mass loss, not of anything unusual about the star's temperature or distance from its companion or position in the galaxy, which means the real question isn't why the Boomerang is cold. The cold follows logically from the physics once you accept the mass loss rate. The real question is why the mass loss rate is what it is. No standard model of how asymptotic giant branch stars shed their outer layers predicts anything close to 1/1000th of a solar mass per year. The models that existed before the Boomerang was studied carefully were off by at least an order of magnitude. Something is driving this star to hemorrhage material at a pace no similar star has ever matched, and the expansion cooling, the record-breaking temperature, all of it traces back to that single unresolved fact. The cold is a symptom, not the cause. And understanding the cause meant figuring out why this star was losing mass at a rate nobody had ever seen before and nobody had a clean explanation for. The shape of the boomerang is a separate mystery from its temperature, and the two mysteries turn out to be connected in ways that took decades to untangle. When you look at the Boomerang Nebula in an optical image, what you see is two lobes of glowing gas expanding outward in opposite directions from a central point, like a bow tie or an hourglass laid on its side. The lobes stretch roughly 1 light-year in each direction from the center. Each one is roughly symmetrical with the other. The whole structure is elongated along a single axis, and the two sides mirror each other with an almost suspicious precision. That symmetry is itself a clue, but for a long time, nobody agreed on what it was a clue to. To understand why the shape is strange, you need to understand how bipolar nebulae are supposed to form. The standard model goes like this. A dying star sheds its outer layers in an expanding shell. In most cases, that shell expands roughly spherically, filling space in all directions more or less evenly, the way a soap bubble expands outward from a central point. But some dying stars have a thick belt of material, a torus or disk, concentrated around their equatorial region. This disk acts like a nozzle. Gas trying to escape sideways runs into dense material and slows down. Gas escaping toward the poles encounters less resistance and moves faster. The result is a bipolar outflow, two jets or lobes of gas moving rapidly in opposite directions, while the equatorial regions stay dense and compact. That is the textbook picture. It explains a large number of bipolar nebulae reasonably well. The Boomerang fits that template in broad outline. It has the two lobes. It has the axis. It has the symmetry you would expect from a collimated outflow. But the details do not cooperate. For one thing, the lobes are unusually elongated compared to other bipolar nebulae. Most hourglass-shaped planetary nebulae are somewhat stubby, with lobes that spread outward in a wide fan. The Boomerang's lobes are narrow, highly collimated, almost tube-like. Something focused the outflow very tightly along a single axis, and the standard disk plus wind model does not easily produce lobes that narrow. You can tweak the model, make the disk denser, make the outflow faster. But the geometry of the Boomerang consistently sits at an extreme that the basic model struggles to reproduce. Then there is the inner structure. Ground-based optical observations from the 1980s and early 1990s showed the outer bipolar lobes clearly. What they did not show was anything complicated happening close to the central star. The region near the center looked relatively unremarkable. When Hubble observed the Boomerang in 1998, finer structure became visible. The inner region, near the core of the nebula, had a different character from the outer lobes. The expansion there was not clean. There was material distributed more broadly, more spherically, in a way that did not match the tight collimation visible farther out. Two different geometries, stacked inside each other. That takes some explaining. One candidate explanation was magnetic fields. Magnetic fields can thread through ionized gas and constrain its motion, channeling outflows along field lines the same way train tracks channel a train. A strong, organized magnetic field aligned with the star's rotation axis could in principle produce tightly collimated jets even without a dense disk. There are other bipolar nebulae where magnetic fields appear to play a significant role. Researchers tried applying magnetic field models to the Boomerang. The math was not impossible, but the field strengths required to produce lobes this narrow, this long, were at the high end of what any physical model of a dying star could plausibly generate. Possible on paper, uncomfortable in practice. Rotation was another candidate. If the central star was spinning rapidly, the centrifugal effect could flatten the stellar wind at the equator and enhance it at the poles. Fast rotation can produce bipolar outflows without requiring a separate disk. This idea has some support from observations of other post-AGB stars. The problem for the Boomerang is the numbers. To produce lobes this elongated through rotation alone, you need very high spin rates, and there is no direct evidence that the Boomerang's central star is rotating that quickly. You can assume it. The assumption is not ruled out, but an assumption that cannot be tested is a weak foundation for a theory. Disk-driven collimation remained the most popular explanation simply because it is the mechanism with the most observational support across other bipolar nebulae. A dense equatorial torus, possibly built up from mass shed in the earlier stages of the star's life, could redirect the outflow into the two elongated lobes. But here, the Boomerang's extreme mass loss rate creates its own complication. The disk, if it exists, would need to be extraordinarily dense to redirect an outflow moving at 164 kilometers per second. Dust grains caught in an outflow that fast do not gently redirect. They get swept. The disk model requires fine-tuning to survive contact with the actual numbers describing this object. What made the shape problem genuinely hard was not that there were no candidates. It was that every candidate had one thing going for it and one thing broken. Magnetic fields could produce the collimation, but not at realistic field strengths. Rotation could produce the geometry, but not without a spin rate nobody could confirm. Disk collimation fit the broad template, but struggled at the extremes the Boomerang consistently occupied. And underneath all of this sat the more uncomfortable question. Why was the outflow so fast and so voluminous in the first place? That question pointed back to the mass loss rate, which pointed to the energy budget, which pointed towards something at the center of the Boomerang that the shape alone could not identify. Each theory for the shape had something going for it and something wrong with it. And the more closely astronomers looked, the more the simple explanations fell apart. The numbers describing the Boomerang's mass loss rate are hard to put in context because nothing else we have ever found matches them. Start with the basic figure. The Boomerang is shedding approximately 0.001 solar masses every year. Written out, that number looks almost modest. But a solar mass is the mass of our entire sun, an object so large that 1 million Earths could fit inside it with room to spare. The Boomerang is losing the equivalent of 1/1000th of that every single year, continuously, pouring material outward into space at speeds that would carry you from Earth to the Moon in under 3 seconds. Every other asymptotic giant branch star we have ever catalogued loses mass at roughly 1/10 that rate, and most lose far less. The Boomerang is not slightly unusual. It is operating in a category of 1. Here is what that rate means over time. Astronomers estimate the Boomerang's extreme outflow has been running for roughly 1,500 years. In that span, a stretch of time that, for human civilization, covers everything from the fall of Rome to today, the star has shed material totaling about 1.5 solar masses. Picture the sun, all of it, converted into a fast expanding shell of cold gas and dust. Now do that again, and then add half of it more. That is what the boomerang has ejected in what is, by astronomical standards, the blink of an eye. The total nebula we observe is not the slow accumulation of a gentle stellar wind over millions of years. It is a catastrophic hemorrhage. Normal stars of this type, late-stage red giants approaching the end of their asymptotic giant branch evolution, do lose mass. That is expected. As a star exhausts its nuclear fuel, its outer layers loosen their grip on the core, and stellar winds carry that material away over millions of years. The process is gradual. The star thins at the edges. A diffuse shell of gas expands slowly outward, and eventually, the cooling remnant core is left behind, surrounded by a gentle planetary nebula. This is the standard ending, and it fits the models that stellar physicists have refined for decades. The boomerang does not fit those models. Its rate is 10 times too high, its velocity is too fast, and its temperature is too cold to be explained by the same gentle wind mechanism that produces ordinary planetary nebulae. What the extreme mass loss is actually doing to the star is, in a word, devastating. As the outer layers are stripped away, the interior is progressively exposed. Deeper material, hotter and denser, becomes the new outer surface. The star is being peeled. Each layer that goes carries energy and momentum with it, and the layers that remain behind are under different pressure conditions than before. The internal structure of the central object is being reshaped in real time, not over geological spans, but over centuries. It is the astronomical equivalent of watching something come apart, not in an explosion, but in a sustained and relentless unraveling. This creates a question that turns out to be surprisingly hard to answer. What is actually driving the mass loss at this rate? Standard stellar wind theory ties mass loss to a combination of radiation pressure, pulsation, and the opacity of the stellar atmosphere. Dust grains in the outer layers absorb radiation from the star's core and are pushed outward, dragging gas along with them. This mechanism works. It explains the mass loss in every normal AGB star we have studied. For the boomerang, the math stops working. Run the numbers with standard inputs: stellar luminosity, mass, temperature, opacity, and the predicted mass loss rate comes out roughly 10 times too low. Something else is contributing energy to the outflow, something the standard wind model does not account for. Several mechanisms were proposed. One idea was that the star's pulsation cycle had become extreme, driving large amplitude oscillations that periodically launched shells of material outward. There is evidence for this kind of behavior in very luminous AGB stars, and a few show enhanced mass loss during particularly energetic pulses. But even the most extreme pulsating AGB stars fall well short of the boomerang's rate. Pulsation alone is not enough. Another idea involved magnetic fields channeling material preferentially along the polar axis, which connects loosely to the bipolar shape. But this explains geometry, not magnitude. The total amount of material being ejected is still far too high for magnetic collimation alone to explain. The outflow velocity adds another layer of difficulty. At around 164 kilometers per second, the gas being driven out of the boomerang is moving faster than the escape velocities of most stellar environments at this evolutionary stage. Standard radiation-driven winds produce much slower outflows, typically tens of kilometers per second for stars of similar luminosity. The speed of the boomerang's wind suggests that the energy source is not just radiation pressure from a normal stellar photosphere. Something is adding a large additional kick. And when you ask what can impart that kind of velocity to that much material over that sustained a period, the standard single-star toolkit runs out of answers quickly. There is also the question of duration. A brief burst of extreme mass loss could be explained by a thermal pulse, a runaway helium shell flash deep in the star's interior that temporarily boosts luminosity and drives enhanced outflow. Thermal pulses happen. They produce brief episodes of elevated mass loss, followed by quieter periods. But 1,500 years is not a brief burst. It is too long for a single thermal pulse and too sustained for anything in the standard pulsation catalogue. The energy source has to be large, consistent, and operating over a timescale that single-star physics struggles to supply. For years, the explanation for the extreme mass loss sat just out of reach, waiting for a telescope powerful enough to look directly into the heart of the thing. In 2013, a new set of instruments turned toward the Boomerang, and what they returned changed the picture in ways nobody had fully anticipated. For roughly 2 decades after Sahai and Nyman measured that extraordinary temperature, the best images of the Boomerang came from Hubble. Those images showed a striking hourglass shape, 2 opposing lobes of gas expanding outward from a central point, bright at the edges and dark through the middle, like a bow tie stretched across several light years of space. Astronomers built their models around that picture. The shape was unusual, the temperature was unprecedented, but the basic geometry seemed clear enough. 2 lobes, 1 star, an extreme but mappable object. That was the picture in 2012. It was largely wrong. The instrument that overturned it sits in the Atacama Desert of northern Chile, at an elevation of roughly 16,500 feet, where the air is thin and dry enough that radio waves from the cold universe pass through with almost no interference. ALMA, the Atacama Large Millimeter/Submillimeter Array, is not one telescope. It is 66 separate antennas spread across a plateau the size of a small city, all working in coordination, combining their signals to produce a single image of extraordinary resolution. When all 66 dishes lock onto the same target, the effective diameter of the instrument stretches to more than 10 miles. No single dish of that size has ever been built. The trick is that the signals from each antenna arrive at slightly different times depending on their position, and sophisticated computers combine those delays to reconstruct what a dish 10 miles wide would have seen. The result is a radio telescope more powerful than anything that existed before it. What makes ALMA specifically useful for something like the Boomerang is the wavelength it observes. Optical telescopes see visible light, the narrow slice of the electromagnetic spectrum your eyes were built for. Visible light is scattered and blocked by dust. Cold molecular gas, the kind filling the Boomerang's outer regions, emits almost no visible light at all. It is essentially transparent to Hubble. Millimeter wave radiation is different. Cold molecules like carbon monoxide emit at very specific millimeter wavelengths as they rotate and release energy, and ALMA is exquisitely sensitive to those emissions. Where Hubble sees glowing dust lit by scattered starlight, ALMA sees the cold gas itself, its distribution, its velocity, its temperature, its density. The 2 telescopes are not competing. They are seeing different things entirely. Raghvendra Sahai, the same astronomer who had measured the Boomerang's temperature in 1995, led the 2013 ALMA observing campaign. His team aimed the array at the Boomerang and began collecting data. What came back surprised them. The hourglass structure that Hubble had captured in visible light was real, but it was only part of the story. The ALMA data showed that surrounding the bright bipolar lobes was a much larger, much colder structure that optical images had missed entirely. It was roughly spherical. It was enormous. And it was moving at a completely different speed from the material in the lobes. This matters enormously. In a simple bipolar nebula, the material throughout the structure should reflect a consistent history of outflow from the central star. Different speeds at different locations can tell you about different ejection events, a faster wind catching up with a slower one, or material pushed sideways by a jet. What the ALMA data suggested was not a refinement of the simple bipolar story. It suggested the Boomerang had experienced at least two distinct phases of mass ejection, and those phases had produced physically separate structures with different geometries, different velocities, and different temperatures. The older, outer structure was something the Hubble images had not shown because it was too cold to glow in visible light. Think of it this way. You are standing in a dark room and you turn on a flashlight. The beam shows you the furniture directly in front of you. You conclude the room contains a couch, a table, and a lamp. Then someone turns on the overhead light and you realize the room is 3 times as large as you thought, and there is an entire wall of bookshelves behind you that the flashlight never reached. The Hubble images were the flashlight. ALMA was the overhead light. The velocity data was equally revealing. When astronomers measure the spectrum of gas in a nebula at radio wavelengths, they can detect the Doppler shift in the emission lines. Gas moving toward Earth compresses the wavelength slightly. Gas moving away stretches it. By mapping those shifts across the face of the nebula, you can reconstruct a picture of how the gas is moving in 3 dimensions. The ALMA measurements showed that the large outer shell and the inner bipolar lobes were not simply different parts of the same outflow. Their velocity patterns were inconsistent with a single ejection history. Something had changed dramatically in the Boomerang's mass loss behavior at some point in the past, and the 2 structures were the physical record of that change. The inner lobes, the ones responsible for the extreme cooling, were moving faster and appeared younger. The outer spherical shell was slower and appeared older. That sequence suggests an early period of relatively slower, roughly symmetric mass ejection, followed by something that drove a far more extreme and directional outflow. What caused the transition was not written in the data. The ALMA observations could describe what existed. They could not yet say why it existed. That question sat at the center of everything the 2013 results raised. The Boomerang's extreme temperature record had been attached to a relatively simple picture of one cold hourglass in space. The ALMA data showed the picture had at least 2 layers, and the colder and more extreme of those layers, the inner bipolar structure driving the record temperature, was not the whole nebula. It was a component embedded inside something larger and older and structurally different. The data that came back from ALMA was not a refinement of the existing picture. It was a different picture entirely, and it raised a question nobody had thought to ask. What ALMA found inside the Boomerang was a second structure that the earlier optical images had hidden completely. For decades, astronomers had looked at the Boomerang through optical telescopes and seen 2 lobes of cold gas pushing outward in opposite directions, like a slow-motion explosion frozen in space. That picture seemed complete enough. 2 lobes, 1 central star, 1 catastrophic outflow. The model was strange, but at least it was a model. Then the ALMA data came back. Inside those lobes was something else entirely. A shell of gas that was warmer, moving differently. Shaped in a way that suggested it had been ejected at a completely different time, under completely different conditions. The structure is roughly spherical. That is the first thing that makes it strange. The outer bipolar lobes are elongated, directed, shaped like an hourglass with its waist cinched tight around a central engine. The inner shell is not like that. It expands outward in all directions more or less equally. The way a single star shedding material through a slow stellar wind is supposed to behave. The 2 structures are sitting inside each other like a ball inside a football. They have different temperatures, different velocities, and different ages. When astronomers ran the numbers on the expansion speeds, the picture that came back was hard to ignore. The spherical shell was moving at roughly 35 kilometers per second. The bipolar outer lobes were moving at around 164 kilometers per second. Though, see are not 2 phases of the same event, those are 2 events. Here is what that means. The spherical inner shell almost certainly represents an earlier period in this star's life, a slower, gentler mass loss phase that proceeded the way stellar evolution textbooks say it should. A star on the asymptotic giant branch, shedding its outer layers gradually, building a roughly round envelope of expelled gas over a long period of time. That is the standard picture of how a star like this dies. And for a while, that was apparently what the Boomerang's central object was doing. Then something changed. The bipolar outflow began, faster, colder, more directed, and on a completely different scale. The slower spherical shell was already out there when it happened. The new faster outflow pushed through it and beyond it. The hourglass shape that the optical images had always shown. This changes the central question. Before the ALMA data, astronomers were asking why the boomerang was so cold. After the ALMA data, they were asking something slightly different and considerably harder. They were asking what event had occurred to turn a standard, gradual stellar wind into a catastrophic bipolar explosion, when exactly that transition happened. The 2-component structure is not just a geometric curiosity, it is evidence of a before and an after. Something triggered the shift. Whatever that something was, it transformed the boomerang from an ordinary dying star into the coldest known object in the universe. There was a further complication. The spherical inner shell, once astronomers could actually measure it separately from the outer lobes, turned out to be warmer than expected. Not warm in any comfortable sense, not warm enough to be visible in optical light or to support chemistry in any meaningful way, but warmer than the outer bipolar lobes. Not uniformly cold the way the 1995 measurements had implied the entire nebula was. Parts of the inner shell showed temperatures above the cosmic microwave background. Some regions were sitting closer to 10 or 12 Kelvin, still brutally cold, but no longer touching the extreme floor the boomerang was famous for. The extreme cold, the 1 Kelvin measurements that had stunned the community, was concentrated in the outer bipolar outflow, not distribute, evenly across the whole structure. This sparked a genuine scientific debate. Some researchers argued that the original temperature measurements had been correct for the entire system, as understood at the time. that the ALMA data was simply showing where the cold was actually located with more precision than before. Others argued that the colder regions were smaller in volume than anyone had assumed. That had implications for how much mass was actually involved in the extreme cooling and whether the mass loss rate calculations needed to be revised. If the cold volume was smaller, the total amount of matter at 1 Kelvin was less than the earlier models had suggested. That rippled backward into the estimates of how fast the star had been losing mass and how long the catastrophic phase had been running. Neither side of that debate declared victory cleanly. The ALMA data was precise, but the boomerang is a complex three-dimensional structure being observed as a two-dimensional projection on the sky. Extracting exact volumes and temperatures from millimeter wave emission lines requires assumptions that can be argued over. What the debate settled into was this: the bipolar lobes are extremely cold, probably close to 1 Kelvin in the fastest moving regions. The inner spherical shell is warmer. The boundary between the two components is real and measurable, and the distinction matters enormously for understanding what physical process is actually driving the cooling. This was because a process that cools only the bipolar component is a different process than one that chills the entire nebula uniformly. What the two-component picture did not do was solve the original mystery. It deepened it. The extreme cold was still there, still the most extreme temperature recorded in a natural setting anywhere in the universe. The extreme mass loss rate was still there, still without a clean explanation in standard stellar wind physics. And now there was an additional layer, evidence of two distinct ejection events, one ordinary and one catastrophic, implying that at some point in this star's recent history, something had dramatically changed. The boomerang still held the record for the coldest known place in the universe, but the record was now attached to a more specific and more puzzling structure than anyone had mapped before. When astronomers started working through what could possibly drive mass loss at the rate the boomerang was producing, one explanation kept rising above the others. Not a stronger stellar wind, not an unusual magnetic field, not some quirk of the star's internal chemistry. The explanation that kept surviving scrutiny was simpler and more dramatic than any of those. The boomerang is not one star. It never was. At some point in the recent past, in astronomical terms, two stars became one. The energy released by that collision is what has been driving everything strange about this object ever since. To understand why this idea gained traction, you have to think about energy. Stars lose mass through stellar winds. Stellar winds are powered by radiation pressure, light pushing outward against the outer layers of the star. For a star in the final stages of its life on the asymptotic giant branch, that radiation pressure can produce impressive winds. But there are limits. The mathematics of single-star evolution sets a ceiling on how fast a star can drive material outward. The boomerang blows past that ceiling by a factor of roughly 10. When you run the numbers for a single star of this type and this luminosity, the mass loss rate you get back is nowhere close to what we actually observe. The energy budget doesn't balance. Something is adding energy to the system that a lone dying star simply cannot supply on its own. A binary merger can supply it. When two stars spiral inward and merge, the gravitational energy released in that process is enormous. It is not a gentle event. Think of it less like two soap bubbles touching, and more like a controlled detonation happening deep inside a stellar atmosphere. The energy that gets dumped into the surrounding gas in a short period of time is enough to blow material outward at velocities that no stellar wind could match. The outflow speed of the boomerang sits around 164 kilometers per second. That is fast. For comparison, the solar wind leaving our sun moves at somewhere between 400 and 800 kilometers per second. But that wind is extremely thin. The boomerang's outflow is moving at high speed and carrying enormous mass. The combination of velocity and mass requires a power source that mergers can provide and single-star winds cannot. The outflow velocity itself is one of the stronger clues pointing toward a merger. Normal stellar winds accelerate gradually as radiation pressure builds up over time. The speed profile of the boomerang's outflow looks different. It looks impulsive, as though something injected a large amount of energy into the system over a relatively short window, rather than building up gradually over thousands or millions of years. This is what a merger event would produce: a sudden injection of energy, a violent rearrangement of the stellar structure. Then an expanding shell of material moving outward at high speed as the record of that event. The two-component structure that ALMA revealed fits this picture as well. The inner spherical shell, moving at lower speeds and appearing warmer, looks like the older outflow from before the merger, material the star had been shedding through normal stellar winds over its lifetime. The outer bipolar lobes, colder and faster, look like the aftermath of the merger itself. Two distinct ejection events, two distinct structures, sitting one inside the other like nested layers. That kind of layering is exactly what binary merger models predict. First a slow spherical wind, then a catastrophic bipolar ejection triggered by the merger event, expanding outward faster than the older material and eventually overtaking and surrounding it. What makes this hard to confirm is that we cannot see the companion. If there is a companion star still orbiting, it is hidden inside the dust and gas at the center of the nebula. If the merger has already completed, there is no companion left to find, just a single stellar remnant that now carries the mass and angular momentum of both original stars. Distinguishing between an ongoing interaction and a completed merger using current instruments is genuinely difficult. The central region of the boomerang is opaque at optical wavelengths. Even ALMA, which sees through the cold molecular gas, cannot resolve the central object clearly enough to settle the question of what is actually there. There are hints, though. The geometry of the bipolar lobes is not perfectly symmetric. One lobe is slightly brighter than the other. The central axis shows a small tilt that some researchers have interpreted as the signature of a precessing system, which would suggest the merger has not fully settled, or that angular momentum from the original binary orbit is still working its way through the remnant. Precession of this kind has been observed in other post-merger candidates and in binary systems where mass transfer is ongoing. It is not proof of a companion, but it is consistent with one. Researchers have also examined the chemical composition of the outflow for clues. Merger events and mass transfer episodes between stars can dredge up material from the interior of one or both stars and mix it into the ejected gas. If the boomerang's outflow shows chemical signatures that don't match what a single star at this evolutionary stage should be producing, that is evidence that the material has been processed through the interior of a second object. The chemical analysis is ongoing, and the results are not yet clean. But the early indications are that the composition of the outflow is unusual in ways that are harder to explain with a single star model. The merger hypothesis also explains the shape more naturally than the alternatives. A binary system has a preferred axis, the rotation axis of the orbit. When material is ejected by a merger, it tends to be flung outward preferentially along the poles of that orbital axis, while the denser, slower material near the equatorial plane collimates the outflow into two opposing lobes. This is precisely the geometry of the boomerang. No separate collimating disk needs to be invoked. No magnetic field configuration needs to be fine-tuned. The shape follows naturally from the physics of a merger occurring inside a cloud of its own previously ejected material. The leading picture now involves not one star dying, but two stars colliding. The boomerang is the still expanding record of that collision, caught in the act. The boomerang is cold and strange, but it is not the only nebula in the sky that looks like it was designed by forces we do not fully understand. About 2,300 light-years away, in the constellation Monoceros, there is an object that has been confusing astronomers for more than 50 years. It does not hold a temperature record. It is not the largest or the brightest thing in the sky. What makes it remarkable is its shape. A shape so geometrically precise and so unlike anything else we have catalogued that when researchers first got a clear look at it from space, they genuinely struggled to explain what they were seeing. The red rectangle was found in 1973 during a rocket-based infrared survey called the AFCRL High Star Survey. The discovery was essentially a side effect of scanning the sky for bright infrared sources. The object stood out because it was radiating strongly in wavelengths associated with warm dust. At that point, from the ground, it looked like a faint reddish smear. The name came from its appearance through early telescopes, a reddish rectangular patch of light that didn't quite match the expected round profile of a star or the diffuse glow of a typical nebula. The designation HD 44179 refers to the central star system catalogued in the Henry Draper catalogue. But nobody calls it that. It is the red rectangle. The name stuck because the shape stuck with the people who first saw it. What Hubble eventually showed, in images taken during the 1990s and refined further after servicing missions, was that the rectangle was not actually a rectangle at all. From space, the true shape of the nebula is an X. Two cone-shaped lobes of gas and dust extend outward from the central star in opposite directions, touching at the middle like two funnels placed tip to tip. The reddish glow comes from hydrocarbon molecules fluorescing in the ultraviolet light of the central stars, a chemical process that makes the nebula shine in a color almost no other object in the sky produces in quite the same way. But the X shape, as strange as it is not the strangest thing about it. Running across both lobes at regular intervals are bands of brighter emission, parallel lines of glowing gas stacked one above the other, crossing the cones like the rungs of a ladder. No other nebula known to science shows this feature. Astronomers trying to explain the rungs eventually landed on an answer that raised as many questions as it answered. The rungs appear to be shells, individual ejection events from the central star system, each one a separate burst of material thrown outward at intervals of roughly a few hundred years. Because we happen to be viewing the red rectangle almost exactly edge-on, those shells don't look like shells, they look like lines. What you are actually seeing when you look at the ladder is a series of smoke rings seen from the side. The mechanism that produces the rungs is not fully settled, but the leading explanation involves the binary stars at the center. The red rectangle is not built around a single star. At its heart are two stars orbiting each other once every 10.5 months, a period short enough that the two objects are gravitationally pulling on each other in ways that matter. That interaction appears to have driven the formation of a thick torus of dust concentrated around the system's equatorial plane. Think of it as a dense ring of material encircling both stars at their waist. When material gets ejected from the system, that dust torus acts as a nozzle. Gas that tries to escape through the equatorial plane runs into the torus and gets blocked. Gas that escapes through the poles faces no such barrier. The result is a bipolar outflow, two jets of material shooting in opposite directions, creating the X shape. This kind of funneling is not unique to the red rectangle. Bipolar nebulae show up fairly regularly in catalogues. What is unique is that the outflow is not steady. The ejection events are episodic, separated by long gaps of relative quiet. Each burst produces a distinct shell expanding outward through the nebula. Laid edge-on, those shells become the ladder. The spacing between the rungs gives astronomers a way to estimate how often these eruptions happen and how long ago each one occurred. The calculations suggest the outermost rungs were produced several thousand years ago, and the process is still ongoing today. There is a chemical dimension to the red rectangle that sets it apart even further. The nebula is rich in polycyclic aromatic hydrocarbons, complex carbon-based molecules that glow in specific infrared wavelengths when energized by ultraviolet light. These molecules are significant because they are among the building blocks that appear in meteorites and in the interstellar medium, connecting the chemistry of dying stars to the raw material of planetary systems. The red rectangle is essentially a factory for complex organic chemistry, running for thousands of years and broadcasting the products in every direction. The central binary is itself in an interesting evolutionary phase. One of the two stars is a post-asymptotic giant branch object, a star that has already shed much of its outer material and is moving toward becoming a white dwarf. The companion is a main sequence star, still on its normal hydrogen-burning track. The interaction between a dying star and an active companion is exactly the kind of configuration that generates complex, non-spherical structures. The mass transfer between them, the gravitational tides, the shared envelope of gas, all of it feeds back into the system and shapes the nebula being built around it. No other nebula in the known sky has the same structure. The consensus now is that two stars built it together in a process that neither could have produced alone. In 1786, William Herschel pointed his telescope at a spot in Draco and found a glowing disk of gas that he described simply as a curious nebula. He catalogued it and moved on. At the time, there was no framework for understanding what a planetary nebula actually was. No way to measure its distance, no way to know what was inside it. Herschel had stumbled onto one of the most physically complex objects in the sky. From his vantage point, it looked like a faint smudge. That gap between appearance and reality would define the Cat's Eye Nebula for the next 2 centuries. NGC 6543 sits roughly 3,300 light-years away in the constellation Draco. In a small telescope, it presents as a bright, compact disk with a faintly greenish glow. Visually, it is striking, but the appearance gives almost nothing away. The real complexity of this object is invisible at low resolution, packed into a structure that requires large apertures and space-based instruments to unravel. What looks like a neat oval of glowing gas is, in fact, a nested series of shells, jets, shockwaves, knotted filaments woven together in a three-dimensional architecture so intricate that researchers have spent decades trying to build a coherent model of how it formed. What makes the cat's eye remarkable is not just that it is complex. It is that the complexity is layered, like a record of events written in gas and light, each layer corresponding to a different episode in the star's history. The first real indication that the cat's eye was hiding something came in 1864. William Huggins pointed a spectroscope at it and became one of the first people to study the spectrum of a nebula. What he found was not the absorption spectrum of reflected starlight, but bright emission lines, proof that the object was a cloud of hot, ionized gas rather than a distant star cluster or solid body. That measurement helped establish the entire category of planetary nebulae as a class of object. NGC 6543 was not just the first of its kind to be closely examined. It was the object that told astronomers this kind of thing existed at all. That history alone would make it significant. The structure underneath that history makes it extraordinary. In 1994, Hubble turned toward the cat's eye, and what the images showed stopped people cold. The simple disk was not a disk. It was a series of nested shells surrounding a bright central region. Inside that central region there were jets, there were knots. There was a point-symmetric structure, meaning the pattern on one side of the nebula mirrored the pattern on the other side when rotated 180 degrees around the central star. That kind of symmetry is not random. It is a signature. It means something with a defined axis, something with directional memory, produced those features. A single star shedding its outer layers in a simple spherical wind does not produce a point-symmetric pattern. Whatever made the cat's eye was more complicated than that. The jets were one of the first clues pointing toward a companion. High-speed streams of gas extending outward from the central star along a specific axis are difficult to explain without something breaking the spherical symmetry of the system. One strong candidate is a companion star pulling material from the central object and launching jets along its rotation axis. The jets in the cat's eye lie roughly perpendicular to the equatorial ring structure inside the nebula. That is exactly what you would expect if a companion were driving outflow along one axis, while a dense equatorial disk of material funneled the main wind along another. No direct observation has confirmed the companion, but the geometry of the nebula keeps pointing toward it. Then there are the rings. 11 or more concentric shells surround the bright inner structure of the cat's eye, evenly spaced and roughly circular, like ripples expanding outward from a stone dropped in still water. Each ring represents a separate episode of mass ejection from the central star. The spacing between them corresponds to periods of roughly 1,500 years between pulses. This is not a star dying in a smooth, continuous exhale. This is a star pulsing. Something in the interior of the object, at regular intervals across thousands of years, caused the outer layers to surge outward in a burst before settling back down. Then it happened again, and again. The rings are the physical record of that process, expanding outward at different speeds, gradually separating from each other as they travel, preserving in T air-spacing the entire tempo of the star's late evolution. This is what researchers mean when they call the cat's eye a fossil record. The word fossil is precise here. Just as a fossil preserves the shape of a living thing long after the thing itself has changed beyond recognition, the concentric rings of NGC 6543 preserve the timing and character of ejection events that happened thousands of years ago. The star at the center is now a hot, compact white dwarf. The outer rings are the remnants of earlier, cooler, puffier versions of that same object, shed layer by layer as the star contracted and heated. Reading the rings backward in time is, in principle, like reading a biography. Each shell is a chapter. The precessing jet model adds another dimension to this. If the jet responsible for the point-symmetric features was not fixed along a single axis, but was slowly wobbling, precessing the way a spinning top precesses when it begins to slow down, then a single jet moving through a full rotation over thousands of years would produce the kinds of curved, sweeping features seen at the periphery of the cat's eye's gas lobes. That model fits. It does not prove the companion exists, but it requires something to drive the precession. A companion's gravitational influence is the most natural explanation anyone has found. 2 centuries of observations have only added more layers to the mystery. The cat's eye remains one of the most complex planetary nebulae anyone has ever examined. The nearest planetary nebula to Earth sits in the constellation Aquarius. When you point a large telescope at it in the right light, it looks like an eye the size of several light years staring back at you. The Helix Nebula, catalogued as NGC 7293, sits roughly 650 light-years from Earth. That is the same distance as Betelgeuse. The coincidence is worth pausing on, because that proximity is what makes the helix so scientifically valuable. When you are 650 light-years away from something that stretches nearly 3 light-years across, you can see details that would be completely washed out in a more distant object. The Helix is not necessarily the strangest planetary nebula we know of. It is the one we can study most closely. Every time we have turned better instruments toward it, the level of strangeness has gone up. The popular nickname came from a single image. In November of 2002, the Hubble Space Telescope released a mosaic photograph of the helix assembled from multiple exposures. The result looked so much like a giant eye that it spread across the internet almost immediately. The blue-green inner ring, the reddish outer halo, the bright central dot of the white dwarf remnant combined into something that looked designed. People called it the Eye of God. The name stuck. But the image that created the nickname also contained something that had nothing to do with the aesthetics and everything to do with the science. When astronomers looked at the helix image carefully, they saw structure inside the inner ring that nobody had expected to find in any planetary nebula, let alone this one. There were knots, thousands of them, dense, compact pockets of gas arranged through the inner region of the nebula, each one trailing a faint streamer of material pointing away from the central star. The streamers stretched outward like comet tails. That is exactly what astronomers began calling them, cometary knots. Each one is roughly the size of our solar system. Each one is a pocket of cold molecular gas, dense enough to persist against the ultraviolet radiation streaming outward from the hot white dwarf at the center. The hot radiation is trying to destroy them. The density of each knot is high enough that the outer layer ablates away while the core survives. The tail forms from that ablated material being swept outward. There are estimated to be somewhere around 20,000 of these knots in the inner ring alone. This raised an immediate question. How does a dying star shed its outer layers and produce tens of thousands of discrete, structured clumps instead of a smooth expanding shell? Standard models of planetary nebula formation assume a fairly continuous outflow, stellar winds blowing material outward over thousands of years in something approximating a sphere. The helix does not look like that. The helix looks like it was shredded. Something about the way the material was ejected, or the way the fast inner wind collided with the slower outer material, broke the expanding shell into fragments. The leading explanation involves instabilities at the boundary between different outflow speeds. The fast wind from the newly exposed stellar remnant slamming into the slower material that was shed early. The collision creating a rippled, unstable front that fragments into knots. But replicating the exact structure computationally has proven difficult, and the knots themselves are still not fully understood. The helix also has a two-disc structure that took decades to confirm. The nebula is not a simple ring. It consists of two roughly perpendicular discs of gas, each one tilted at a different angle to our line of sight, overlapping in projection to create the appearance of a single ring when viewed from Earth. The inner disk is dominated by highly ionized, hot gas. The outer disk is older, cooler, and dominated by the cometary knot structure. Fitting these two components together into a single coherent formation model has not been straightforward. It adds to the sense that the helix, despite being our nearest example, has not given up its full explanation yet. Then came JWST. In 2024, the James Webb Space Telescope turned its infrared instruments on the helix and returned images of a detail that previous telescopes simply could not resolve. What JWST showed, more clearly than anything before it, was the sharp transition zone between the hot ionized gas near the white dwarf and the cold molecular material in the outer regions. This boundary is not gradual. It is abrupt in a way that surprised the team studying it, the hot gas from the stellar remnant pushing outward, meeting the cold outer shell, the two regions existing in immediate proximity without blending smoothly. Where they meet, the hot material punches through the cold shell in irregular plumes. Knotty structures at the interface that had been hinted at before, but never seen in this resolution. The outer regions held a separate surprise. Far from the hot inner zone, in the coldest parts of the outer halo, JWST detected pockets of molecular hydrogen. Cold molecular hydrogen does not survive just anywhere. It requires temperatures low enough and densities high enough to shield the molecules from destructive radiation. The presence of molecular hydrogen in the outer helix suggests that the chemistry happening there is more complex than simple ionized gas. Conditions in those outer pockets may support the formation of larger molecules, the kind of carbon-bearing chemistry that serves as the foundation for organic compounds. A dying star in its final dispersal, laying down the chemical conditions for something that could eventually participate in planet formation and the larger cycle of cosmic chemistry. That is what the helix represents when you step back from the individual findings. It is the closest version we have of what the Sun will produce roughly 5 billion years from now. A white dwarf at the center, an expanding shell of gas and dust, cometary knots fragmenting off the inner ring, a boundary between hot and cold regions, sharp enough to see from 650 light-years. And in the outer halo, complex chemistry already beginning in the dispersed material. The Helix is the most detailed portrait we have of a sun-like star's death. The more detail we add, the stranger that portrait becomes. There is a nebula in Aquarius that through a small telescope looks like a miniature version of the planet Saturn, complete with an oval disk and faint extensions on either side that resemble rings. That resemblance is not accidental, and it is not subtle. Point almost any backyard telescope at the right patch of sky, and the shape is immediately recognizable. Two faint handles extend outward from a glowing greenish oval. The whole arrangement is close enough to Saturn's profile that when William Herschel found it on September 7, 1782, the comparison was the first thing anyone thought of. The name stuck, and for the next 2 centuries, that image, a neat oval with handles, was essentially the whole story. It was a planetary nebula. It glowed. It looked tidy. Astronomers had a category for it and moved on. The category was wrong. Not completely wrong, but wrong enough that when modern instruments finally looked at NGC 7009 in genuine detail, what came back was almost unrecognizable as the same object. The simple oval hid a system of nested structures, so layered and so physically distinct from each other that researchers had to invent new vocabulary just to describe the parts. Herschel found something real in 1782. He just had no way of knowing what he had actually found. Herschel was working with a telescope of his own design in the garden outside his home in Datchet, England. He logged the object carefully, noted its unusual appearance, and moved on to the next target. Over the following century, other astronomers added observations, better position measurements, rough estimates of size. Early spectroscopic data that confirmed the nebula was made of gas rather than unresolved stars. The first real hint that something more complicated was going on came from higher resolution imaging in the latter half of the 20th century. The handles, the structures Herschel had noted, and which gave the Saturn comparison its power, turned out to be more than simple extensions of the main nebula. They had different spectral properties than the central oval. They were behaving differently. Researchers gave them a formal name, ansae, from the Latin word for handles, or why they glowed the way they did, while the rest of the nebula glowed differently around them. To understand what the Saturn nebula actually is, you need a picture that has nothing to do with what you can see through an eyepiece. The VLT, the Very Large Telescope operated by the European Southern Observatory in the Chilean desert, carries an instrument called MUSE, the Multi-Unit Spectroscopic Explorer. MUSE does not take a single photograph. It takes thousands of spectra simultaneously, covering every point across the face of a target at once. When researchers turned it toward NGC 7009, they were mapping it chemically, physically, kinematically, tracking what each part of the object is made of, how hot it is, how fast it is moving, how that changes from one region to the next. What the MUSE data revealed was staggering. The Saturn Nebula is not one structure. It is at least 8 distinct structures nested inside each other, each one operating under different physical conditions. There is an internal shell at the center, surrounding the bright white dwarf remnant that powers the whole system. Around that is the main shell, the dominant glowing body visible to small telescopes. Beyond that lies an outer shell, and then a large diffuse halo extending well past the visible edges. Those are just the large-scale components. Within and between them are the ansae, those distinctive handle structures, now understood to be low excitation, likely shocked layers of gas near the poles. Connecting the main shell to the ansae are regions called streams, running along the pole R-axis at high excitation, and wrapped around the equator of the system, embedded in the outer shell. Is a feature described as a pseudo-ring, a belt of medium to low excitation gas that circles the waist of the nebula. The Muse observation was also notable for a different reason entirely. It produced the first successful dust map of the interior of any planetary nebula. Each of those components sits at a different temperature. Each has a different ionization state, meaning the atoms within them have lost different numbers of electrons to the radiation field from the central star. Each is moving at a different speed. The internal shell is hot and highly ionized, close to the energetic white dwarf. The halo is cooler, older, moving more slowly. The record of material ejected longer ago when the star was at an earlier stage of its death. The ansae are cold relative to the streams, even though they sit at similar distances from the center. The pseudo-ring is a separate kinematic feature from the shells around it. None of these components follow a simple gradient. The structure is not just an onion with layers. It is an onion where each layer has its own chi, mystery, its own history, its own physical story. What drives a dying star to build something this complicated? The honest answer is that no single model fully accounts for it. Binary companions are a candidate. Interactions between two stars can break the spherical symmetry of a simple wind and create the elongations, polar structures. Equatorial concentrations visible in NGC 7009. The episodic nature of mass ejection from the central star is another factor. Material shed at different times and different speeds piles up into distinct shells rather than blending into a smooth gradient. Magnetic fields and rotation complicate the picture further. Every mechanism leaves a partial fingerprint on the structure. Isolating which mechanism produced which feature has occupied researchers for years without a clean resolution. The broader lesson of the Saturn Nebula is the same lesson the other strange nebulae keep delivering. An object that looks clean and simple in one wavelength through one instrument at one level of resolution is not necessarily simple. It is just incompletely observed. The Helix looked like a ring. The Saturn Nebula looked like a planet. Both of those impressions were correct at the scale they were measured and wrong at every deeper scale. The apparent simplicity of a bright oval in a small telescope hides more than a dozen separate structures at different temperatures and speeds. The full picture still does not fit any single clean model. In the summer of 2022, the first science images from the James Webb Space Telescope came back to Earth. Within months, it was clear that every assumption about what nebulae looked like was going to need updating. The telescope had been in planning for decades. Engineers had folded its 18 gold-plated mirror segments into a configuration small enough to fit inside a rocket fairing. Launched it on Christmas Day 2021, then spent 6 months unfolding it, cooling it, calibrating it at a point in space roughly 1 million miles from Earth. The scientific community had waited a long time. What they got back, when the data finally started arriving, was not confirmation of what they already knew. It was revision after revision after revision. The Southern Ring Nebula was one of the first targets. It sits about 2,500 light-years away in the constellation Vela. Before JWST, it looked like a fairly standard example of its kind. Two nested shells of glowing gas surrounding what appeared to be a single central star. Astronomers had classified it and moved on. When JWST pointed its infrared instruments at the Southern Ring, the picture that came back stopped people cold. The faint central star, the one that had been largely ignored in previous studies because it appeared dim and unremarkable, turned out to be a white dwarf. And it was not alone. Right next to it, completely invisible in optical wavelengths, was a companion star. That companion had been actively dumping material onto the white dwarf for hundreds of thousands of years. The dust and gas spilling off that interaction had shaped the entire nebula. The shells, the rings, the asymmetries that previous astronomers had catalogued without explanation. They were not random. They were the record of two stars building a structure together. The Southern Ring Nebula. That is technically the same object as NGC 3132 had been studied for generations. Nobody had seen this. JWST found it on its first real look. The NGC 3132 data went further. The JWST images revealed not just the companion star, but two distinct dust disks around the central star system, orbiting at different angles and interacting with each other in ways that had shaped the outflow geometry of the whole nebula. These disks had been completely invisible before infrared observations at JWST's sensitivity were available. They are made of cold dust that emits no visible light. From the ground, from Hubble, even from Spitzer, they were simply not there. The moment JWST found them, the shape of the Southern Ring Nebula made sense in a way it never had before. Two disks, two stars, an extended history of interaction, and every ring and shell in the nebula was the physical signature of that history, recorded in gas and dust spread across light-years of space. Then JWST turned toward the Ring Nebula. This is one of the most famous objects in the northern sky, found in Lyra, the small constellation anchored by the bright star Vega. Amateur astronomers have been observing the Ring Nebula for centuries. Through a moderate-sized backyard telescope, it looks like a small smoke ring, a greenish oval with a faint star at the center. It is beautiful, and it is, by astronomical standards, well understood. A sun-like star shed its outer layers, leaving a hot white dwarf behind. The ultraviolet radiation from that remnant ionized the surrounding gas into a glowing shell. Clean, simple, explained. The 2023 JWST observations suggested something considerably more complicated was hiding inside that clean story. The outer halo of the Ring Nebula, the region beyond the main glowing ring where the nebula fades into surrounding space, turned out to contain roughly 20,000 individual clumps of cold molecular gas. 20,000. Each one is a dense pocket of hydrogen and other molecules that somehow survived inside the expanding outflow. Cool enough that JWST could detect them in infrared, but almost completely invisible to every previous instrument. They are organized in radial streaks pointing away from the central star, like spokes on a wheel. The fine structure within them is still being mapped. Nobody predicted 20,000 molecular globules in the outer halo of the Ring Nebula. The models did not put them there. They were found because JWST looked. The pattern across every target has been the same. Objects that looked structurally simple in optical observations carry hidden layers that only become visible in the infrared. Cold companions that were contributing mass and shaping outflows for hundreds of thousands of years were invisible because they radiate in the wrong part of the spectrum. Molecular chemistry at the cold edges of nebulae, where complex molecules are forming out of the expanding gas, had been theorized but rarely confirmed in detail. Now JWST is finding it routinely. In the Helix Nebula, those cold pockets of molecular hydrogen in the outer ring, the ones that earlier observations had hinted at, came back in JWST data with a clarity that allowed direct measurement of chemical abundances. Some of those regions have conditions suited to the formation of organic molecules. The outer shell of a dying star is producing the raw ingredients for complex chemistry. JWST is reading the inventory. What this means for nebula science is not subtle. The Saturn Nebula's extraordinary internal complexity, mapped by Muse on the Very Large Telescope, showed what is possible when you look carefully. JWST is now doing the equivalent of that mapping for dozens of objects at once. Every time it returns a result, the conclusion is the same. The previous best image was leaving most of the story out. Companions were hidden. Dust structures were invisible. The chemical complexity at the edges of these objects was uncharted. The instrument is forcing a wholesale re-examination of objects that researchers considered understood. Every nebula JWST has examined closely has come back stranger than the previous best image suggested. The catalogue of targets is only a fraction of the way through. The deeper you look at the strangest nebulae, the more often the same thing turns up at the center of the explanation. Not a specific temperature or a specific shape. Not a particular mass or a particular age. The thing that keeps appearing over and over at the heart of the most unusual and most extreme objects in this entire category is a second star, a companion, something orbiting close enough or merging violently enough to completely reshape what the dying star produces when it finally lets go. This is not a coincidence that a handful of researchers noticed in a handful of cases. The statistical picture has been building for 2 decades, and by now it is difficult to dismiss. Studies of planetary nebulae with bipolar or highly asymmetric shapes consistently find binary central stars at rates far higher than you would expect from chance alone. Some surveys put the fraction of complex, non-spherical planetary nebulae with confirmed or strongly suspected binary cores above 80%. That number is not settled science yet. The observations are hard and the sample sizes are limited. But the direction of the evidence is not ambiguous. When a dying star makes something strange, there is usually another star involved. The mechanisms connecting companions to strange shapes are not mysterious once you lay them out. Take the simplest case first. A star in its final phase of life swells into a red giant, expanding outward until its outer layers reach the gravitational territory of an orbiting companion. At that point, the companion starts pulling material off the giant through a process called mass transfer. The giant is losing material faster than it would on its own. The companion is gaining it. The whole system becomes dynamically unstable. What gets ejected into space is not a smooth spherical wind in all directions. It is shaped by the orbital geometry of the pair. Material leaving near the orbital plane gets concentrated there. The outflow along the poles, away from the plane, escapes more easily. T result is exactly what you see in the boomerang, the red rectangle, and the cat's eye. Two lobes expanding outward from the poles, pinched at the equator by a dense ring of material that the binary interaction deposited there. Tidal forces add another layer. Even before mass transfer begins, a close companion raises tides on the surface of the giant. Those tides deposit angular momentum into the outer layers of the star, spinning them up. A faster rotating star sheds material differently than a slow one. The equatorial regions feel stronger centrifugal effects, and the outflow becomes naturally flattened. You get a disk, or a torus, or a thick equatorial concentration, and that structure then acts as a nozzle for everything that follows. The bipolar shape is a downstream consequence of this early angular momentum transfer. The companion didn't have to do anything dramatic. It just had to be there, close enough, long enough. Then there are the mergers, and those are a different category entirely. When a companion doesn't just orbit, but actually spirals inward and merges with the giant's core, the energy released in that event is enormous. The outer envelope of the star can be ejected in a catastrophic burst rather than a gradual wind. The outflow speeds are higher than any standard stellar wind model predicts. The mass loss rate spikes far above what the star could produce on its own. This is almost certainly what happened inside the boomerang. The outflow velocity of around 164 kilometers per second and the mass loss rate roughly 10 times higher than anything seen in comparable single stars both point toward an impulsive event. Something released a large amount of energy on a short timescale. A merger is the only mechanism in the current playbook that fits that description. For decades, none of this was in the playbook at all. The standard models of stellar evolution were built around single stars. You started with a mass, ran the physics forward, and got a predicted outcome, a planetary nebula of a certain type, expanding at a certain speed, with a central white dwarf of a certain brightness. The models worked reasonably well for simple, round, symmetric nebulae. Those cases were treated as the normal ones. The bipolar cases, the asymmetric cases, the extreme cases, like the boomerang, were treated as oddities, requiring special explanations. What JWST and the generation of surveys before it have made harder to ignore is that the oddities are not rare. They may actually represent the majority of the interesting objects in this class. The simpler, rounder nebulae might be the ones with genuinely isolated progenitors, and those might be a minority of the overall population. The implication is uncomfortable, but increasingly unavoidable. The stellar evolution models that worked for the simple cases were not wrong exactly. They were just incomplete. They were describing a subset of dying stars and treating that subset as the whole picture. What changes in practice when you accept the binary picture? Observers now look at every complex nebula with the explicit question of whether there is a companion hidden at the center. Sometimes the companion is visible directly. More often it is inferred through the shape of the nebula, through the kinematics of the outflow, through infrared excess light that suggests a disk left behind by an interaction. The search has become systematic in a way it was not before. When the JWST images of the Southern Ring Nebula came back and showed evidence of a second star driving the whole structure, that result landed with the weight of confirmation rather than surprise. Researchers had been expecting to find something like it, the picture is still incomplete. The sample of confirmed binary central stars in planetary nebulae is smaller than the statistical evidence suggests it should be, partly because companions can be faint, close, and difficult to resolve against a bright nebula. The orbital period distribution is not well characterized. The frequency of mergers versus surviving binaries is not settled. There is substantial work left to do, and the answers will matter not just for nebula science, but for understanding how common binary interaction is across all stellar deaths. The conversation about how Sun-like stars die has shifted in the last 2 decades, and the shift comes down to one revision. Most of them are not doing it alone. Pull back from the individual cases, and a pattern emerges that none of them suggests on its own. The boomerang, the red rectangle, the cat's eye, the Helix, the Saturn Nebula. Each one was treated for years as a peculiar exception. An interesting data point: a strange object sitting at the edge of the catalogue, noted and then set aside while researchers turned back to the objects that fit the standard picture. What the last 3 decades of observation have quietly revealed is that the strange objects were never exceptions. They were windows. Each one was showing a version of stellar death that the tidy models had glossed over. The more telescopes we pointed at them, the more clearly that picture came into focus. The first thread running through all of them is one the Betelgeuse story touched on as well. Stars do not lose mass smoothly. This is the assumption embedded in most stellar evolution codes going back decades, that as a star ages, it gradually sheds material through a slow, continuous wind, like a candle burning down. The boomerang demolished that assumption with a single number: a mass loss rate roughly 10 times higher than any other known object in its class. But the boomerang did not demolish it alone. The cat's eye has 11 or more concentric rings, each one representing a pulse of ejected material spaced roughly 100 to 300 years apart. That is not a candle burning down. That is a series of explosions separated by long silences. The red rectangle shows the same signature. The ladder-like rungs in its structure are episodes of mass ejections seen edge-on, stacked like a record of irregular heartbeats. The Helix, seen up close by JWST, shows thousands of dense knots in the inner ring, where ejected material hit previously shed shells and compressed. Each knot is evidence of a boundary between 2 different ejection events arriving at different speeds. Everywhere you look, the evidence points the same direction. Stars die in bursts as well as drips. The bursts are where most of the interesting physics lives. The second thread is hidden structure. Every single one of these nebulae looked simpler before someone looked closely. The Saturn Nebula appears through a small telescope as a gentle oval with faint extensions. That image hides more than a dozen nested substructures at different temperatures and velocities. The boomerang looked like a faint, elongated smudge in ground-based optical images until ALMA came back with data showing a spherical inner shell completely invisible to previous instruments. The Helix looked like a single expanding ring until the cometary knots appeared. The cat's eye looked like a disk until Hubble resolved the nested rings. The pattern repeats so consistently that it has effectively become a prediction. Point a better instrument at any of these objects. You will find something the previous instrument missed. What this means practically is that our census of nebula types has been built partly on ignorance of resolution. Objects we classified as simple may be complex objects we lack the tools to fully see. The third thread follows from that one. The mass loss models that currently exist were calibrated against observations that were, in many cases, not detailed enough. If the boomerang's total cold mass was estimated from optical images that missed the spherical inner shell, then the estimate was wrong. If the cat's eye's total ejected mass was integrated from images that did not resolve the individual rings, then that number is approximate at best. Multiply this problem across hundreds of objects in stellar evolution catalogues, and you get a systematic bias. The models were built by averaging observations that averaged over structure that we could not yet see. That is not a criticism of the researchers who built them. It is a consequence of working with instruments that existed at the time. But it means the correction is not a small one. The underlying mass loss rates and their episodic nature feed directly into predictions about final stellar mass, WIT, a dwarf composition, the chemical material returned to the galaxy. Get those wrong, and downstream predictions in galaxy evolution models accumulate the same error. The fourth thread is the binary question, which the previous section covered directly. But there is a specific implication worth drawing out here. If a large fraction of the strangest nebulae are produced by binary interactions, mergers, mass transfer, tidal coupling, then the strange nebulae are not rare events. Binary stars are common. Most stars in the galaxy are found in pairs or higher order systems. If binary interaction produces the extreme mass loss that makes these objects stand out, then extreme mass loss events may be occurring throughout the galaxy at a rate our single-star models have never accounted for. The boomerang may not be uniquely strange. It may just be the closest example of a process that is happening in thousands of other systems we have not yet studied in the same detail. That possibility has a specific consequence. Stellar evolution theory has treated the asymptotic giant branch, the phase of life where these nebulae form, as relatively well understood. Mass loss rates go into the models. White dwarf masses come out. Planetary nebulae form and fade in predictable ways. The strange nebulae are collectively applying pressure to that settled confidence, not by invalidating the whole picture, but by pointing to the specific places where the picture was drawn from a sample that favored the ordinary and missed the extreme. The objects that looked simple were the ones we built our models on. The ones that looked strange got filed as exceptions. And now the exceptions are accumulating fast enough that the category itself is under pressure. Not a few unusual cases to explain away, a growing body of evidence that the smooth, single-star continuous wind picture of stellar death was an idealization. Reality is messier and more violent than that idealization allowed. The strange nebulae are not the exceptions to the rule. They are the rule. The simpler objects were what misled us. The boomerang is not frozen in its current state. It is actively changing, and the object astronomers observe in a few thousand years will not be the same object we see today. To understand where the boomerang is headed, you have to understand where it currently sits in the life cycle of a dying star. Right now, the central object, whatever it is, single star or the merged remnant of two, is still relatively cool by stellar standards. It has not yet shed enough of its outer layers to expose the hot, compressed core underneath. That core exists. It is waiting. And the moment it becomes exposed to the surrounding gas, everything about the boomerang changes. The ultraviolet radiation that a hot stellar remnant produces is not a gentle glow. It strips electrons from hydrogen atoms across enormous distances. It heats gas. It ionizes entire shells of material that were sitting quietly in the cold. When that process begins in the Boomerang, the temperature of the surrounding nebula will rise, and the record the Boomerang currently holds, coldest known place in the observable universe, simply ends. This is not speculation. It is the standard pathway that all objects of this type eventually follow. What makes the Boomerang unusual is how extreme its current cold phase is, which means the transition when it arrives will be equally dramatic. Astronomers classify the Boomerang right now as a protoplanetary nebula, an object caught between the end of active mass loss from the central star and the beginning of the hot ionized emission phase that produces a true planetary nebula. Most protoplanetary nebulae spend only a few thousand years in this transitional stage before the central remnant heats up enough to start ionizing the gas around it. A few thousand years sounds long. On a human timescale, it is. On an astronomical one, it is barely a breath. The question is, how far along that transition the Boomerang currently is? The honest answer is that astronomers are not certain, partly because the central star is difficult to observe directly. The surrounding gas and dust obscure it. The ALMA data from 2013 gave a cleaner picture of the structure than any optical image had, but the central source itself remains partially hidden. What researchers can say is that the central remnant appears to still be in the cooler phase. Its ultraviolet output has not yet reached the threshold needed to ionize the outer lobes. When it does, those outer lobes will begin to glow. Not faintly, brightly. The cold bipolar outflow, which today is visible only because it scatters light from the central star, will transform into a self-luminous emission nebula. What would the resulting planetary nebula look like? Based on the current structure, you would expect something with a strong bipolar morphology, two opposing lobes of ionized gas extending outward from a hot central remnant. The shape already exists. The cold outflow has been carving it for the last 1,500 years. What changes is the lighting. Right now, the Boomerang is lit from within by scattered starlight, dim and diffuse. In its ionized form, the same structure would glow in the sharp emission lines of hydrogen and oxygen, visible in the false color images that make planetary nebulae look so vivid in astronomical photographs. The inner spherical shell that ALMA detected, the older, slower outflow that preceded the current bipolar phase, would likely produce a different emission signal. From the faster outer lobes, giving the resulting nebula a layered appearance, something like the nested rings visible in objects like the cat's eye. There is also the question of the cold. 1 Kelvin is the number that has defined the Boomerang in every article and textbook entry since Sahai and Neiman published their measurement in 1995. That number will not survive the transition. Ultraviolet radiation from a hot white dwarf remnant can heat surrounding gas to tens of thousands of Kelvin. The same material that currently sits at 1 degree above absolute zero would climb to temperatures that no longer qualify as unusual. The record disappears not because anything has been disproven, but simply because the physics of the object will have changed. The cold is a product of the current expansion rate and the current radiation environment. Change the radiation environment, and the cold goes with it. There is something almost counterintuitive about this. The most extreme temperature object we have ever found is extreme specifically because it has not yet reached the phase when it becomes ordinary. The cold is a symptom of an in-between state. Most objects that reach this stage don't cool as dramatically as the boomerang did, because most don't lose mass at the rate the boomerang did. But the end point, hot, ionized, glowing, is the same for all of them. The boomerang is taking an unusual route to a fairly standard destination. Watch a particular spot in Centaurus for long enough, and long enough here means thousands of years, not lifetimes, and you would see the faint smudge of the current nebula gradually brighten as the central remnant heats up. The lobes would begin to light from the inside. Color would emerge in wavelengths that optical telescopes can record directly. The nebula would grow in apparent size as the gas continues to expand outward. And the temperature at the center of the structure, which today is the coldest measured anywhere in the universe, would climb toward the tens of thousands of Kelvin, typical of a mature planetary nebula. What we are looking at right now is a window. The boomerang in its current form is a temporary object, a brief configuration of gas and dust and cold that exists only because we happen to be watching at exactly this moment in the star's history. Earlier, the mass ejection was still ongoing. Later, the radiation will change everything. Right now, for a few thousand years out of a stellar lifetime of millions, the conditions align to produce something with no parallel anywhere in the sky. The coldest known place in the universe is a temporary phenomenon, a brief chapter in the story of a dying star, and the chapter is already turning. Here is something that tends to stop people when they first hear it clearly stated. Every nebula covered in this video, the boomerang, the helix, the cat's eye, the red rectangle, is not just a distant spectacle. Each one is a preview. The sun will do this. Not soon, not in any timescale that touches a human life or a civilization, or even the entire recorded history of our species on this planet, but in roughly 5 billion years. The same sequence of events that produced those objects will run its course on the star at the center of our solar system. The sun is not special in this regard. It is a low-mass star of average size and average composition. Stars like that have a known fate. What these nebulae are showing us is exactly what that fate looks like, in detail, close enough to examine. The sun right now is doing what it has been doing for about 4.6 billion years. It is fusing hydrogen into helium in its core, releasing energy at a steady rate, holding itself together against its own gravity through that pressure. This phase of its life is called the main sequence. The sun has roughly another 5 billion years left on it, when the hydrogen in the core finally runs out. The core will begin to contract under gravity while the outer layers expand dramatically. The sun will swell into a red giant, growing large enough that its outer envelope could potentially reach the current orbit of Earth. Mercury will be gone. Venus will be gone. What happens to Earth is still debated, but the planet as anything recognizable will not survive. The inner solar system, everything we have ever called home, will be consumed or scorched beyond recognition. After the red giant phase, the sun will not explode. It does not have enough mass for that. Instead, it will shed its outer layers in a series of expanding shells, driven by stellar winds and pulsations similar to what we see in Betelgeuse today, but slower and less violent. Those shells will move outward into surrounding space, lit from within by ultraviolet radiation from the hot core left behind. What remains at the center will be a white dwarf, a compressed remnant roughly the size of Earth, but with a mass close to what the Sun has today. That white dwarf will be extremely hot at first, radiating intensely. The surrounding gas will glow in response. From a distance of several hundred light-years, it will look like a planetary nebula. It will look in many ways like the Helix. The Helix Nebula sits 650 light-years from Earth. Astronomers often describe it as the closest look we have at a Sun-like star completing this exact process. Its central white dwarf has a surface temperature of around 100,000 Kelvin. Its surrounding shells of gas extend across several light-years. The cometary knots in its inner ring, thousands of dense cold pockets of molecular hydrogen, formed as the hot outflow from the central remnant crashed into the slower, older material ejected during the red giant phase. This collision is part of what the Sun's death will produce as well. The shockwave moving through the former solar system, the nested shells at different temperatures and velocities, the boundary between old slow gas and fast hot outflow. The helix is not a metaphor for our future, it is an example of it. The question of what shape the Sun's nebula will take is more complicated. A spherical nebula is the simplest outcome. For a single star without significant companions, that is the default prediction. But the evidence from objects like the boomerang, the cat's eye, the red rectangle keeps pointing toward binary interactions as the driver of complexity. The Sun does not have a stellar companion. What it does have is Jupiter. Several researchers have proposed that Jupiter's gravitational influence could play a role in shaping the Sun's mass loss during the red giant phase, potentially introducing an asymmetry that nudges the outflow away from a perfect sphere. The mass of Jupiter is about 1/1000th the mass of the Sun, which sounds insignificant. But at the scale of a distended red giant with loosely held outer layers, tidal effects become relevant. Whether Jupiter's influence is strong enough to produce a bipolar nebula, or even a noticeably asymmetric one, remains genuinely uncertain. What seems more likely, based on the current understanding of mass loss physics, is that the Sun will produce something relatively symmetric, a modest, round planetary nebula, not unlike the simpler objects in the catalogues that astronomers looked at for decades before the strange ones forced a reconsideration. It will probably not reach the extremes of the boomerang. It will not have the catastrophic mass loss rate or the expansion velocity that drops the temperature to 1 Kelvin. The Sun is not losing a companion through a merger. It is just running out of fuel on its own, quietly, by the standards of the objects we have been discussing here. The result will be beautiful and relatively unremarkable by the standards of this neighborhood of the galaxy. But here is what will be left behind. What connects the Sun to the boomerang and the helix and every other planetary nebula in the catalogue? All the material the Sun ejects in its final stages, the carbon, the oxygen, the nitrogen, elements cooked in its core over billions of years, will spread into surrounding space. Those atoms will mix with the interstellar medium. Over millions of years, they will be incorporated into new clouds of gas and dust. Eventually, some of that material will end up in a new star system, a new protoplanetary disk, new worlds. The stuff being flung outward by the boomerang right now is following the same path. This is how the galaxy recycles itself, one dying star at a time, each one returning what it borrowed from the medium around it. Whatever nebula the Sun eventually leaves behind, it joins the same slow enrichment of the galaxy that the boomerang is already participating in. one dying star's contribution to the raw material of whatever comes next. The picture of stellar evolution that existed 30 years ago was already complicated, and the strange nebulae have been steadily making it more so. The standard model of stellar evolution is not a single equation. It is a framework built over roughly a century of observation and theory, and for most of its history, it has treated stars as fundamentally solitary objects. A star forms from a collapsing cloud of gas. It burns through its fuel on a predictable schedule. It sheds its outer layers and dies. The timescales and final products depend on mass, and the models for calculating those outcomes have become increasingly precise. For decades, that framework worked well enough that astronomers trusted it. The strange nebulae have been eroding that trust, one measurement at a time. One of the specific places the framework breaks down is mass loss. Stellar evolution models need accurate mass loss rates to make useful predictions. If you get the mass loss rate wrong, everything downstream is wrong. The final mass of the remnant, the total amount of material returned to the interstellar medium, and the chemical composition of that material. For decades, the mass loss rates plugged into the models were derived from observations of relatively well-behaved stars, averaged over long timescales, and treated as smooth, continuous processes. The Boomerang Nebula is an argument against all three of those assumptions at once. Its mass loss rate is roughly 10 times higher than any comparable star astronomers had previously measured. And the evidence from the cat's eye, the red R, rectangle, and the helix all points in the same direction. Mass loss is not smooth, it is episodic. Stars don't bleed slowly and steadily. They pulse, they burst, they shed material in discrete events separated by quieter periods, and the models have not fully caught up to that reality. The numbers matter here. When a model assumes a smooth wind carrying away stellar material at a modest rate over millions of years, the star ends up with a certain final mass. Change that to episodic bursts, brief episodes where the star loses mass at catastrophic rates, like the Boomerang, and the final mass is different. A different final mass means a different white dwarf. In cases where the star is massive enough to explode, a different pre-supernova mass means a different explosion. The shock wave has different energy. The remnant has different properties. These are not small corrections. They propagate through the entire prediction chain, and the uncertainties compound at every step. Then there is the binary problem, and it is a bigger problem than the mass loss rates alone. Current stellar evolution codes, the software that simulates how stars live and die, still treat the majority of stars as single objects. The case for doing that was always somewhat convenient rather than strictly justified, and the strange nebulae have been dismantling it methodically. A high fraction of all planetary nebulae with complex shapes, bipolar lobes, multiple shells, asymmetric outflows, appear to have binary stars at their centers. The Boomerang almost certainly does. The red rectangle confirmed one. The cat's eye is strongly suspected. The southern ring. Nebula's JWST observations confirmed a companion whose interaction shaped the whole structure. These are not rare exceptions. They are turning out to be the norm, which raises an uncomfortable question about what the simpler, more symmetric nebulae are hiding. When you add binary companions to the models, the behavior changes in ways that matter. A companion star can strip material from a swelling giant, transferring mass and angular momentum in ways that alter both stars simultaneously. A companion in a close orbit can tidally distort the giant's outer layers, driving up the mass loss rate dramatically and helping explain objects like the Boomerang. And if the two stars merge, the energy released is enormous, enough to drive the kind of catastrophic ejection that produces extreme cold and extreme outflow velocities in a single impulsive event rather than a gradual wind. Mergers and close interactions don't just affect the nebula, they affect the stellar remnant. A merger can produce a white dwarf more massive than either star would have left on its own. In more massive systems, the difference between a neutron star and a black hole can come down to how much mass was lost before the explosion, and binary interactions are one of the things that decide that. Galaxy chemical evolution is caught up in this too. The interstellar medium is seeded by dying stars. Every element heavier than helium that forms in stellar interiors eventually gets returned to space through stellar winds, planetary nebulae, and supernovae, and that material becomes the raw ingredient for the next generation of stars and planets. The models that predict how much of each element gets returned and when are built on those same mass loss rates and remnant masses. Get the mass loss wrong, or miss the binary contribution entirely, and the chemical enrichment history of the galaxy comes out wrong. The abundance of carbon, nitrogen, oxygen in the interstellar medium, the molecules that eventually end up in planetary atmospheres, depends on how accurately we track what dying stars are actually releasing. The strange nebulae are a correction notice for those predictions. What makes this particularly difficult to solve is that the timescales are inaccessible. We cannot watch a single star die from beginning to end. We observe snapshots, different objects at different stages, and piece together a sequence. When the snapshots include objects as extreme as the Boomerang, they force a re-examination of every stage in the assumed sequence. Was the calm, slow wind phase actually calm? Was it continuous, or was it punctuated by events we are only now learning to recognize? These are questions the nebulae raised, and the models are still trying to answer. The strangest nebulae are not anomalies in an otherwise well-understood field. They are the specific places where the gaps in our understanding have become impossible to ignore. We started with a simple claim. There is a place in the sky colder than outer space. Not colder than a laboratory freezer. Not colder than a comet drifting through the outer solar system. Colder than the background radiation left over from the Big Bang itself. 1 Kelvin. A number that should not belong to any natural object, anywhere. And yet there it sits, in the southern sky, in a constellation most people in the northern hemisphere have never seen, doing something the textbooks said was not possible. Every object in this video started out the same way. Simple, explainable. A disk of glowing gas in Draco, a ring in Aquarius, an elongated smudge in Centaurus. The cat's eye looked like a clean oval of light for nearly 2 centuries before Hubble came back with the nested rings, the jets, the knots of shocked gas, the point-symmetric structure that no single star model could account for. The Helix looked like a thin ring until JWST showed thousands of cometary knots trailing cold molecular gas through the inner cavity. The red rectangle looked like a reddish blur until someone resolved the X and saw the rungs. Every time, the first image lied. Not maliciously, just incompletely. That is the pattern. It runs through all of this. The universe does not volunteer its structure. You have to earn each layer of it with a better instrument, a more careful question, a measurement someone had not thought to take yet. Raghavendra Sahai did not go to the JWST telescope in 1995 expecting to find the coldest place in the universe. He was following up on an unusual object. He asked a careful question. The answer came back strange. That is how most of the real discoveries in this video happened. Not with a grand theory predicting something exotic, with someone looking more closely at something already known and finding out the known thing was different than anyone thought. The boomerang still does not have a confirmed answer at its center. The binary merger hypothesis fits the energy budget better than a single dying star does. The two-component structure ALMA found in 2013 is consistent with two separate ejection events, possibly two separate objects interacting. But the companion, if there is one, has not been directly detected. The core remains hidden behind the cold expanding gas. Whatever is driving the outflow at 164 kilometers per second, whatever mechanism bled off 1.5 solar masses in 15 centuries, is still technically an open question. The leading theory is compelling. It is not confirmed. Meanwhile, the nebula keeps moving. At 164 kilometers per second, the outer lobes are pushing farther into the surrounding interstellar medium with every passing year. In a few thousand years, the central remnant will begin to heat and ionize the surrounding gas. The cold will start to lift. The record for coldest known place in the observable universe will eventually belong to something else, somewhere else, and the boomerang will join the long catalogue of warm, glowing planetaries that populate the galaxy. The most extreme thing about it will be gone. What will remain is a shape, a record of the violence that built it, and the slowly fading chemical signature of a star that shed its outer layers into the raw material of whatever comes next. 5,000 light years away, the boomerang keeps expanding outward into the dark, the coldest thing in the observable universe, and at its center, something we still cannot fully see keeps driving it forward.